Hello, so today I'm going to explain to you a very nice and simple derivation of Unruh radiation that I published in my book, Physics from the Edge, back in 2014, and which I hope will help explain the concept a little bit. Okay, so I'll go to the whiteboard. I'll start with Heisenberg's uncertainty principle, which states that the uncertainty momentum of an object, quantum object, times the uncertainty in position is always greater than or equal to h bar. Okay, so the big difference between the derivation I'm going to show you and the normal ones is that I'm including a bit of quantized inertia in this, in that this parameter here, the uncertainty in position, I'm actually going to get from special relativity. Imagine you have an object here which is accelerating to the right, and I usually draw acceleration vectors as double arrows. It sees a horizon to its left there. This is because the light cannot catch up with this object which is accelerating away from it. And this is something that's predicted by special relativity, and the distance to it is c squared over a. And I'm going to take this distance to be the uncertainty in position in Heisenberg's uncertainty principle. So there I'm boldly mixing relativity with quantum mechanics. And it makes some kind of sense because the uncertainty in position of this object has to be less than the distance to the horizon because it can't see beyond the horizon. So this is the only distance it knows. So we can write immediately that delta p times c squared over a is greater than or equal to h bar. Okay, so straight away we can say that dp is greater than or equal to h bar a over c squared. So already you may be able to see the similarity to Unruh's formula appearing. So because we're talking about radiation, then the energy is equal to the momentum times the speed of light. So we can rewrite this. P is E divided by the speed of light. So we get the energy is h bar a over c, because the c's cancel. And also because Unruh radiation is radiation and is thermalized, we can say that the energy is equal to Boltzmann's constant times the temperature. And therefore, you can write that T has got to be greater than or equal to h bar a over c k. And this is now very similar to Unruh's formula that he derived in a different way, which was T is h bar a over 2 pi ck. So these things are fairly similar. And I think this explanation is quite simple and perhaps easier to intuitively understand. Okay, so thanks so much for listening, and till next time.